wanted to have an opportunity here on October the 8th, 2020, to continue our Meet the Scientist series. We don't often get the opportunity to introduce you to our network of SBIR, Small Business Innovative Research, staff and scientists, but today we get that opportunity. I'm going to be talking to Elliot Grunewald from Vista Clara. Elliot and the other team members from Vista Clara have been long-term collaborators with myself and others on the project, going all the way back to Rifle, but now here in the beautiful East River watershed. You can see it's a glorious day to be out here working. So Elliot, why don't you tell us a little bit about the project that you're working on here today?
Sure, yeah, we feel very fortunate to be working at such a beautiful site. All the work that we've been doing out here has been using magnetic resonance sensors that we developed at our company Vista Clara. And these sensors are really powerful for characterizing groundwater systems. And that's because the sensors are able to directly measure the hydrogen that's in the groundwater. So H2O, there are hydrogen that are there that we can directly measure. The physics that we use is very similar to an MRI in the hospital. In an MRI, they're imaging hydrogen in biological tissue, and they can provide information about where that hydrogen is and even the properties of the tissue. So with the tool that's down this well, it's sort of like an inside-out MRI. It is measuring the hydrogen that are in the formation here in shales and in alluvium and colluvium. And we can determine how much hydrogen there is, which tells us how much groundwater there is, or how much porosity the formation is holding, how much water is in the formation. And we also get information about how easily the water will flow through those formations. If we have water that's in very large pore spaces, it has a different signature from water that's in really tiny pore spaces. So hopefully that information can be used to provide the scientists here parameters for their modeling to understand how groundwater and nutrients are going to be moving through the system. So today we're doing borehole geophysical measurements with this inside-out sensor that goes down a well. Previously we've been out at the site using a different version of the sensor where we're just laying large loops of wire on the ground and can image to 100, 200 feet to understand what's going on with the groundwater system at greater depth.
So that's a surface-based measurement, and while you have the ability to actually interrogate the ground to quite deep depths, you actually do lose resolution as compared to a borehole method. Is that correct?
That's right. So with a tool that goes down a well, we get very high precision, very high resolution measurements, but we need to have a well. So we have worked at 3 different wells at this site. We have 3 different 1D profiles. But if we're able, when we've been out with a surface system, we're able to get much more coverage, but again, not with the same degree of resolution and precision that we would have in the borehole.
Excellent. So for reference, we're here at the well we refer to as GUM1, or Gothic Upper Montane. It's a pretty interesting well. It actually sits at the base here of beautiful Gothic Mountain. This is a large talus slope and colluvial slope that overlies shale bedrock. We've got about 20 feet of colluvium and talus overlying a sharp contrast in shale bedrock. Tell us briefly, Elliot, kind of what you saw with the data that sort of discriminates those two regions.
Sure. Well, to us, the shale and the colluvium look very different from one another. The shale has almost no mobile water detected in it except for a small amount of water in fractures, whereas the colluvium, these unconsolidated sediments, we see much higher mobile water contents, much higher estimated permeabilities. So it's obvious that a lot of movement is happening through the shallower sediments, but we've also found within the shales some zones of very isolated fractures that we're targeting with some follow-up flow measurements to try to see just how much flow is associated with those deeper fractures that may be as deep as 100 or 150 feet.
Excellent. Thanks so much, Elliot. Really appreciate the introduction.
Thanks.